This DS represents the second portion of atomic structure, and that is Bohr's theory. What is Bohr's theory? We'll look at that, sure. And remember, this is discussion we are talking about. We are discussing NCERT. So, taking these questions as an excuse, we will not only re-examine Bohr's theory, we will discover the theoretical nuances, and we will have probably an in-depth analysis also as far as these questions permit. So, let's begin the session of NCERT discussion. What is the wavelength of light emitted when the electron in a hydrogen atom undergoes transition from an energy level with n is equal to 4 to energy level with n is equal to 2? Now, within an atom, I am told that there are many energy levels, yes. And see, how exactly are electrons arranged around the atom? Bohr says that there are different levels. N is equal to 1, 2, 3 and 4. And as long as electrons are revolving in these orbits, fixed orbits called stationary orbits, they neither emit nor they absorb any energy. Fine. They emit or absorb only when they jump from one shell to the other or one orbit to the other. In our case, I am being told that the electrons are jumping from n is equal to 4 to n is equal to 2. Now, when they jump from higher orbit to lower orbit, they emit a photon. And this energy of photon, is energy of electron in 4th orbit minus energy of electron in 2nd orbit. You take the energy difference. You take the energy difference of electron in higher shell and lower shell, and the difference of energy can be accounted for by the energy of photon which has been emitted. This is simple Bohr's theory, the theoretical background of Bohr's theory. Fine. Do we have a formula? Yes, we do. This is 1 by lambda, and lambda is lambda of photon. Please don't get confused between de Broglie wavelength of electron, which is also lambda, and photon. I'm clearly writing this. This is equal to RH, which is Rydberg's constant, into Z square 1 upon N2 square minus 1 upon N1 square. That is Rydberg's formula for spectrum. Lambda of photon emitted we have to find. Rydberg's constant is a constant, so we'll just take that. Z. Now, this is a hydrogen atom. Yes, hydrogen atom. So, Z is equal to 1 because Z represents the atomic number 1 upon N2 square. Where it has jumped to 2. So, 1 upon 2 square minus 1 upon 4 square, it has come from N is equal to 4. Rydberg's constant is approximately 10 raised to 7 per meter. Approximately. Actually, is 1.097 something, but roughly this. Can I solve this? Of course I can solve this. How much is that? 1 by 2 square, 1 by 4 minus 1 by 16. Now, 1 by 4 minus 1 by 16, it is simply 3 by 16. So, therefore, lambda photon will be 16 by 3 into 10 raised to minus 7 meters. If you want, if you can give you a more accurate value of Rydberg's constant also, and we can calculate that more nicely. That would give us, let me just do it for you properly. Lambda photon is 16 by 3 into 1.097. Just let me check. Rydberg's constant was in denominator. Yeah, it would be. So that would be minus 7 upon 1.097. This is how it would look like. Let's solve this out. Once with this, so many meters. And this comes out to be 486 nanometer on solving. You want to get to the exact number? How did I calculate? Calculation obviously is left to you. But if you want me to show the calculation parts also, well, I would love to help. This Please remember, although mathematical, but this is very essential part of numerical or physical chemistry, because if you're not comfortable with calculations, you will always be uncomfortable with these chapters. That is why I solve each of them, even the mathematical computations I show, so that you get more comfortable. How do I do it? Let's try this out together. Well, 1.097 approximately is 1.1, and 1 by 1.1 is approximately 0.9. This is roughly 0.9 actually we are talking about. So this is 16 by 3 into 0.9. 16 is 48. So this is 4.8 into 10 raised to minus 7 meter and 480 nanometer. 480 nanometer by gross approximations I get this, and if you do this very accurately you get 486. Well, we happy, we are pretty close. How much energy is required to ionize a hydrogen atom if the electron occupies n is equal to 5 orbit? Okay, compare your answer with the ionization enthalpy of hydrogen atom. Energy required to remove the electron from n is equal to 1 orbit. So I am left with two offers. First of all, I am told that the electron is already present in n is equal to 5, fifth orbit, and I am asked that from fifth orbit, if I have to totally remove it means I have to move it to infinity. Oh wow, just let me write it down. If I write this, it looks like, well, initially, if you remember N1, N2, N1, what is N1? N1 is the initial orbit, N2 is the final orbit. So N1 is given to me as 5, N2 is given to me as infinity. Fascinating. I'm supposed to find energy. Can I find energy of electron in any given orbit? Do I have a formula? Yes, I do. And what is that? Energy of electron in nth orbit is E naught z square by n square. E naught is energy in the first orbit. Okay? And E naught has a value. E naught is minus 13.6 electron volts. I have remembered this value. It's a standard formula which I'm going to use in Bohr's theory. So energy of electron in hydrogen atom or hydrogen-like atom in nth orbit is E naught, which is minus 13.6 electron volts, into z square, z is atomic number, and n is the orbit number. So E5, how much is that? This is E naught into 1 square by 5 square, which is E naught upon 25. Wow, that looks really small. And how much is that? Well, that would be minus 13.6 by 25. Fine. And how much is that? Multiply and divide by 4. So 6 was 24 and 4 ones are 4. Right. So this comes out to be 0.544 electron volts minus. So E5 is so much, and E infinity will be, well, E naught into 1 square upon infinity square, which is 0. This is good. This is easy. Yes. So delta E, change in energy, is E final minus E initial, which is E infinity, minus E5, which is 0 minus 0.544, which is plus 0.544 electron volt. How much of energy is required to ionize a hydrogen atom? Ionization means you move it to infinity. And in this case, if you move this to infinity, my dears, this is the result. So ionization is the first answer which I have obtained is ionization energy for n is equal to 5 is 0.544 electron volts only. Second part, compare your answer with ionization enthalpy of hydrogen atom and n is equal to 1. If you are already in n is equal to 1, now standard ionization energy for H atom is 13.6 electron volt. Why 13.6? Because in first shell the energy is E naught, which is Again minus 13.6. From minus 13.6 you are moving it to infinity, which is 0. So the difference would be 13.6 electron volts. How do they compare? It is only 25th, 1 by 25 times. So you can say that ionization energy in the 5th orbit gets reduced to 1 by 25 times, 1/25th of the energy in the 1st orbit. So it's very small, very elementary, very little as compared to n is equal to 1. Not just that, if we want the answer in joules, can we do that? Yes, we can. Convert this to joules. How shall we do that? 0.544 electron volts correspond to 0.544 into 1.6 into 10 raised to minus 19 joules. Multiply the lovely thing and you will see this comes out to be 8.72 into 10 raised to minus 20 joules. What is the maximum number of emission lines when the excited electron of a hydrogen atom in n is equal to 6 drops to the ground state? This becomes interesting. What does it mean? See, all they're saying is some electrons are present in n is equal to 6. From 6, I have 5, 4, 3, 2 and 1. The maximum number of emission lines means how many different frequencies or wavelengths can be observed. So, a hydrogen atom. So first of all, please remember, you have only single hydrogen atom, you don't have many. Okay. So what are the ways in which electron can fall back? Well, from n is equal to 6, straight it could have fallen back. From 6 to 1. And in that case, you would have said that there is a single photon. The answer would have been 1. But is it the maximum number? No. The maximum would be 6 to 5, 5 to 4, 4 to 3, 3 to 2, 2 to 1. So 1, 2, 3, 4, 5. So 5 photons, if they are emitted, that is the maximum possible number of emission lines you might possibly observe. I am talking about a single hydrogen atom because that is what has been asked. So what is the maximum number of emission lines when the excited electron of this is the keyword here, of a hydrogen atom in n = 6 drops to the ground state? This, my dears, is the answer. 5 different photons are possible. The first photon would be emitted from 6 to 5, then from 5 to 4, second photon, 4 to 3, third photon, 3 to 2, fourth photon, and 2 to 1 would be the fifth photon, one after the other. That is the possibility. Also, there is a beautiful way to get it wrong. What? If you neglect this word A, and you would see that in a number of possible popular internet solutions. If you neglect the word A, that means if you assume that there are many hydrogen atoms, if there are many hydrogen atoms, then you could have one hydrogen atom in which this is happening. I could have had another one in which there is a direct emission. And please note, this photon is different from any of these 5. Yes. Are there not more possibilities? There are many more possibilities actually. Can we count them? Let me help you in counting them. Let me repeat and stress first. The solution to this question is over. The answer is 5. But across the internet, you might find the answer is 15. How do I know this? I know this. Everybody knows this. And why this? I'll tell you how they get 15. Why it is wrong. But I've already told. Single hydrogen atom can just give you this much. If you have more than one, in one of the hydrogen atoms this is happening. In the second one this may happen. In the third one, yes, there is a different possibility. What? I could have this and then this. Oh my God. So what do I get? I get 2 photons here. Then this is also a combination possible. This and this. And then this and this. What nonsense is this? How can you count? See, it's very simple. Mathematically, from n is equal to 6, you could go to 5, 4, 3, 2, 1 directly. So there are 1, 2, 3, 4, 5. 5 photons possible. That is 1. If you're jumping directly from 6 to any orbit, you can get 5 different photons. Okay. Now, from n is equal to 5, if you're again falling down, from 5 you could come to 4, 3, 2 or 1. And please note, this has nothing in common with this. If you're counting like this is same. It becomes problematic. Okay, so you have to, you have to make sure that you're not counting double. But this method which I'm teaching you, you would see that there is no possibility of counting double, because in this case you started with n is equal to 6. And in this case you're starting with n is equal to 5. And 5 is directly going to 4 or 5 to 3 or 5 to 2 or 5 to 1. So there are 4 photons possible. Right? And then n is equal to 4, 3 and 2. From 2 you can go to 1. From 3 you could go to 2 or you could go to 1. From 4 you could go to, 3 or 2 or 1. So you have 5 photons or 4 or 3 or 2 or 1. So 1 plus 2 plus 3 plus 4 plus 5. Well, you add them up and you get how much? 15 photons. Is this the answer? No, this is not the answer. This is the answer given on internet. Popular other edtech sites, etc., the rubbish ones. Why I'm telling you this? So that you don't get confused. Oh my God, there are 10 people offering 15 as the answer and maybe sir didn't know. I know this very well. The only thing is, you should know this is a tricky question. If you have a single hydrogen atom, answer is 5. If you have a sample of hydrogen atoms which has multiple hydrogen atoms, then my dears, the answer would be 15. Can we have a mathematical formula? You can. How exactly? Just clean up the space and write that for you. You can do direct counting like we have done, common sense. But common sense is again a dangerous and a rarer sense. So, can you do it as a formula also? Oh, yes. There are cheap guides which mention formulae and we love that cheapness and brainlessness. So please give us a formula. We can directly calculate. Well, we can do that. How? I'll tell you. I told you a method, now I'll tell you a formula also. If you have n shells, you take any 2 at a time, NC2. Okay, and you get that. That's it. Okay, and how much is NC2? NC2 is, why? Because out of n shells, you take any 2 at a time and exchange the photon between them. And this is a unique photon you will get. This is n factorial by 2 factorial into n minus 2 factorial, which is n into n minus 1 upon 2. Okay. So does this formula fit here? Yes. If n is equal to 6, then 6 into 6 minus 1 upon 2, which is 3 into 5, which is 15. See, we get this. So what is this? Maximum number of photons possible in the spectrum. And spectrum is obtained only when you have multiple atoms. I repeat, I really repeat for a 5th, 6th, 7th time. A hydrogen atom, if this is only a single hydrogen atom, the answer cannot be more than 5. If you have a group of atoms, then you can have the answer as 15. The energy associated with the first orbit in hydrogen atom is minus 2.18 into 10 to the minus 18 joules per atom. What is the energy associated with the 5th orbit? Actually, this is a repeated question within the NCERT text. Why? Just 2 questions back, exactly same question was there with a different grammar. They had first shell and they had 5th shell. The least they could have done is, at least they could have changed 5th to 4th or 3rd or 6th or whatever. But let's do it again. Now it's pretty shameless. E is E naught into Z square by N square. This is the formula. Energy in nth orbit is energy in the first orbit into atomic number, the square, and the level n square, which is the first orbit I am given as minus 2.18 into 10 raised to minus 18 joules per atom. Lovely, right? Into z square, 1 square, by n square, which is 5 square. So what do? I just divide it by 25. That's so stupid. It is. Let's do that. That is 8.78. No, 72, not 8. 8.72. How am I doing it? See, dividing by 25 is very unpleasant. So I will simply multiply and divide by 4. So I can say this is minus 2.18 into 10 raised to minus 18. It's a calculation trick. By 25, I am simply multiplying and dividing by 4. Why? How did you choose the number 4? See, 25 4s are 100. And the easiest multiplication and division is by 10, 100, 1000, etc. You just have to shift the decimal. That's very easy. So now that, see, multiplying by 4 is easy. 18 4s are 72. So I have 0.72 and 8. This divided by 100 into 10 raised to minus 18. Oh my God, this is as lovely as it gets. Yes. How much is this? This comes out to be minus 8.72 into 10 raised to minus 20 joules. Lovely, isn't it? That's it. Calculate the radius of Bohr's fifth orbit for hydrogen atom. Now, this is another very important formula. Radius of nth orbit. Radius of nth Bohr orbit is R0. Okay. Into n square by z. That's lovely. So, R0 is radius of first Bohr orbit, which is 0.529 angstrom unit. So let us just substitute. This is 0.529 angstrom units multiplied by n square. Now fifth orbit is 5 square by 1. Okay, hydrogen atom means Z is equal to 1. How much would that be? That is 0.529 angstrom units into 25. And as usual, since I hate multiplying by 25, I'll just multiply by 4. Okay. Dividing by 4 is still more pleasant, and this makes it 100. So this is 52.9 by 4 angstrom units, or 5.29 upon 4 nanometer. Nanometer is more fashionable, we will write it that way. And how much is that? Can I divide by 4? Even if I'm really stupid, I can, and I believe I'm not that stupid. So 1.3215 nanometers. Oh wow, is this the answer? Well, that does look like the answer. Oh, small 225, right? This is the answer. You can check. A simple answer. Calculate the wave number for the longest wavelength transition in the Balmer series of atomic hydrogen. Well, wave number. What is wave number? Wave number is nu bar, which is 1 by lambda. So I'm supposed to calculate indirectly wavelength of the longest wavelength. Longest wavelength means minimum energy. Okay. In the Balmer series of atomic hydrogen, what is Balmer series? Actually, some scientists have associated their names with certain portions of hydrogen spectrum. You have to remember the meaning of Balmer series. From anywhere, if the electron jumps to n is equal to 2, then we say that the collection of all such photons would collectively be called Balmer series. What? I repeat. From infinity is very big, chalo, fine, na? From n is equal to 6, if you jump to 2, from 5 you jump to 2, 4 to 2, 3 to 2, anywhere to 2, group or collection of all these photons is called what? Is called Balmer series. Oh, that's it. It's just a stupid name associated with some The moment you say Balmer series, it means finally you are falling in n is equal to 2. That match is fixed. That much remembrance you must have, that much thing you must have learnt by heart. Longest wavelength means smallest energy difference. So, amongst these transitions, do you appreciate that which energy difference is the smallest and which energy difference is the biggest? This is maximum energy. And this is minimum energy. Minimum energy means longest wavelength. And this is what has been asked. So the moment they say longest wavelength of Balmer series, Balmer series means finally I am going to have n is equal to 2. And initially I must have had n is equal to 3. From 3 to 2, this is the transition they're talking about. This is the only simple mystery you have to figure out in this question. Once you have this, you just have to substitute in the formula and solve it. We are supposed to find out the wave number. Oh, let's do that. And how shall we? We'll need more space. So I'll just say 1 by lambda, which is wave number also, which is RH. Rydberg's formula I'm using 1 upon n2 square minus 1 upon n1 square. Okay, so Rydberg's constant 1.097 into 10 raised to 7 per meter. Z is 1 square, 1 upon 2 square minus 1 upon 3 square. That looks awfully simple. It is awfully simple. So, what do I get? I get 1.097 into 10 raised to 7, 1 by 4 minus 1 by 9 per meter. This is the wave number, my dear. Can I solve for that? Of course I can. This is 5 by 36 into 1.097 into 10 raised to 7, or I could say this is 10 raised to 6. 10.97, I could take it here, right? Once I make this calculation, I divide this 55 by 36, I get this as the answer. 10 raised to 6 per meter has already come, and on solving this, you get the number 1.5236. What is the energy in joules required to shift the electron of the hydrogen atom from first Bohr orbit to the fifth Bohr orbit? Now, NCERT is absolutely in love with fifth orbit for some strange reason. And what is the wavelength of the light emitted when the electron returns to the ground state? Okay, the ground state electron energy is so much. That's not very problematic. First Bohr to fifth Bohr orbit. So you have n is equal to 1. Lovely. And from there, you are uplifting the electron to n is equal to 5. So you have to supply energy. How much energy? There is some energy in the first orbit, E naught. And energy in fifth orbit is E naught z square by n square, which is E naught by 25. So the difference in energy, delta E, is equal to energy supplied to the electron. In which process? In the process of moving it from 1 to 5. And that would be E5 minus E naught. E5 is E naught by 25 minus E naught, which is 24 by 25 times, minus 24 by 25 times E naught. And how much is E naught? I am given E naught. This is minus 24 by 25 times. E naught is again minus, so minus becomes plus 2.18 into 10 raised to minus 11 ergs. That's not very difficult. Ergs to joules is a straightforward journey. You know the conversion. So you calculate this. This comes out to be 2.093. A little less than 2.18 into 10 raised to minus 11 ergs, which is 2.093 into 10 raised to minus 18 joules. Oh my God, I'm sorry. It's a little ugly, but yeah. This is the answer? Yes, this is the answer. This is the energy that is required. Don't forget, 1 erg is 10 raised to minus 7 joules. This is the conversion we have used, and this is the answer we get. That's the first part. We have used this energy to push it up. And if it falls back, it is going to emit a photon, and the photon also would have exactly the same energy, right? So what about, and they've asked, what is the wavelength of light emitted? So let us find the wavelength of light. Now, energy of photon, we know this is 2.093 into 10 raised to minus 18 joules. We just calculated whatever energy is absorbed from 1 to 5, the same energy will be emitted from 5 to 1 if you go back. This is energy of photon emitted, which will be equal to hc by lambda. The lovely lambda is h 6.626 into 10 raised to minus 34 joule second into 3 into 10 raised to 8 meters per second divided by 2.093 into 10 raised to minus 18 joules. Fascinating. Let's solve this out. How much does that give me? This is 6.626 into 3 by 2.093, all fanciful numbers, into 10 raised to how much? This is 18 plus 8, 26, 26 and 34, that is 10 raised to minus 8 into 10 raised to minus 8 meters. 10 raised to minus 8 meter is as good as 10 raised to minus 6 centimeter. And you have to solve this. 6 is 18, this is 19 point something by 2, 9.51. So the answer comes out to be 9.51 into 10 raised to minus 6 centimeter on solving. The electron energy in hydrogen atom is given by En. I'm given the formula. Now, I already know the formula, but then they are feeling like supplying is the formula. Let them. En is minus 2.18 into 10 raised to minus 18 by n square joules. Fine. Calculate the energy required to remove an electron completely from n is equal to 2 orbit. So, from 2, you are finally moving it to infinity. That is complete removal. You are moving it to infinity. Okay, that is the first part. And then what is the longest wavelength, blah, blah. We will see it later. First, let us solve the first part. What is the energy required to remove an electron from 2 to infinity? That means difference in energy is E infinity minus E2, which is, well, E naught z square by n square when n is equal to infinity minus E naught z square by n square when n is equal to 2. Now, the moment you put infinity in denominator, it becomes 0. So, this is 0 minus 0 minus E naught. So, let's take a look. What does it give me? E naught z square by 2 square. Which, now z is hydrogen atom, z is 1. So, this is minus E naught by 4. And E naught has been given to me. How much is that? That is minus 2.18. Again, please note, minus 2.18. So, this is plus 2.18 into 10 raised to minus 18 by 4 joules. This electron energy in hydrogen atom, this is the energy, extra energy which will be required for ionization. Can I calculate that very easily? That is going to be how much? Well, 4 5s are 20, 21, so 18, 4 4s are 16, 5.45 into 10 raised to minus 19. Oh, am I right? Yes, so many joules. This is the first part. Calculate the energy required to remove an electron completely from n is equal to 4, n is equal to 2. This is the energy. Then they're saying the second part, what is the longest wavelength of light in centimeter that can be used to cause this transition? Now suddenly students start getting doubt, What is the meaning of longest wavelength? What does all this mean? Can we mug up a formula? No. You can mug up, fine, but then first of all you have to imagine this physically, what exactly is happening. See, you have n is equal to 1, you have n is equal to 2, you have electron here, and you find that a photon falls here. This absorbs energy, and this jumps up and goes to n is equal to infinity. Fine. This is what is happening, right? You also calculated the energy of this photon. Yes, we did. Fine, very good. Now the fun part is, when you say longest wavelength, see, it's like this. I have this marker, fine. If I just try some strength, it's a plastic marker, I can break it. Yes, I can. I have that energy. Now, if somebody much stronger than me tries to break it, they also can. If the entire, you can say a mountain falls on this, or big huge boulders fall on this, they can still break it, yes. See, there is a minimum energy required to break this marker, right? If you supply more energy, will it break? Yes, it will break. It will be a waste of energy, but nonetheless, it will be crushed, no doubt. In the same fashion, if you are supplying a minimum energy, can an electron go out? Yes. But if you supply more energy than that, can the electron still go out? Yes, it still can. It still can. And that extra energy will even stay with that electron which has run away. Fine. But if you supply more than a minimum energy, the electron can still be broken away, it can still be pulled away. Right? But if you supply an energy which is less than the minimum, what is the minimum energy? This is the energy we calculated. This is the energy difference from 2 to infinity. So at least give me this much energy so that electron can jump away. If I give you more, you can. It's something like, to buy maybe a chocolate, you need 100 rupees. Fine. Now, if you have 500 rupees, can you still buy a chocolate? Yes, you can still buy that 100 rupees chocolate, and you will be left with extra 400 rupees. That's okay. But can you get the chocolate? Yes. And you are still having extra. So what is the minimum money you need to get the chocolate? 100 rupees. Provided it's a 100 rupee worth chocolate, right? So in the same fashion, when we are talking about this, it's the same story. Why are we using this term like longest wavelength? It is confusing. No, it is not confusing. All it means is longest wavelength means minimum energy. That much you should appreciate at c by lambda, Planck's quantum theory. Now, when I'm talking about what is the minimum energy, why minimum? Because if I supply more energy, I can still pull away electron. I can. But if I give less energy than this, then the electron cannot be completely removed. So there is something called as a minimum energy, but there is nothing called as a maximum energy, because you can give entire universe's energy to this, still it can break away. Not a big deal, right? So minimum energy. And that is why we have longest wavelength. So lambda is E is hc by lambda. Therefore lambda is hc upon E. Yes. So lambda minimum, maximum is hc upon E minimum. You need minimum energy, and reciprocal of that, you will get maximum wavelength. How much is H? 6.626 into 10 raised to minus 34. What is C? C is 3 into 10 raised to 8. By minimum energy, how much is that minimum energy? We calculated there. That was 5.45 into 10 raised to minus 19 joules. Now, this is joules second, this is meters per second. So I can cancel all these units, right? Neat and clean, what do I get? I get 6.626 into 3 by 5.45, lovely numbers, into, now 19 goes up, 19 plus 8, 27, 27 and 34, that makes it 10 raised to minus 7 meters. Oh wow. Or something into 10 raised to minus 5 centimeter, because 1 meter is 100 centimeter. You can put that and you can get this number. If I solve this, how much is this? 6.626 into 3 is approx 20. 20 by 5 would be 4. 5.5 is a little less than 4. It's roughly 18 to 3.647. We have the answer also. So we have the final calculated number. Use it and be happy. That's it. And now we come to an example of de Broglie wavelength. What is that? For the first time, de Broglie talked about the dual nature of matter. He said that there is a wave nature associated with every material particle also. Pretty strange. And then not just that, he gave a formula also for that. And on that formula is based this question. Calculate the wavelength of an electron moving with a velocity of 2.05 into 10 to 7 meters per second. Well, lambda de Broglie is h upon mv. This is de Broglie's formula. And what is this? H is 6.626 into 10 raised to minus 34 joule second by mass 9.1 into 10 raised to minus 31 kg into velocity is 2.05 into 10 raised to 7 meters per second. As lovely as it gets. How much would that be? Well, that would be, let's see, 6.626 by 9.1 into 2.05 into 10 raised to minus 34. 34 by 31 makes it how much? 10 to minus 3, and that makes it 10 to minus 10. So many meters. Oh wow. I'm supposed to calculate that? Of course I'm supposed to. How do I do that calculation? I could do some approximate calculations for you and give you a rough number, and then we'll look at the accurate number. See, 6.626. Now if I assume 6.626 is 6.66666, that is 20 upon 3. Instead of this, I could write 20 upon 3. And please note, I have increased this number a little. So that is one felony I have committed. This is being divided by 9.1. Let me be shameless and make it 9. You have reduced it? Yes, I have. I can increase this a bit. If I have reduced 9.1 to 9, now if you are uncomfortable, you could also do the opposite. Let's jump at 9.1, let us increase to 10. It is much easier to multiply divide by 10. Fine. I have increased it by roughly 10%. So the other one I should decrease also by roughly 10%. 2.05, reduce it, around 1.8 it comes out to be. Fine. So if I just do this, how much do I get? Now this is 1 upon 0.8. 1.8 is 0.55. 0.55 into 2 by 3. 1.1 by 3. That is how much? 0.3. Yeah. 11 by 3 would be 3 3 is 9, 10, 11, 3, 6, 7. Right. So it's very crudely I get this is around 3.67 into 10 raised to minus 11 meters. This is what it looks like. It's a very crude calculation. Again, let me tell you, I've calculated here. That is rough. Let us look at the accurate answer. 3.548. Not very bad. We guessed around how much? 3.67 as an approximate answer after doing a lot of drastic approximations. 3.6, I get 3.5 here. I am very happy. It's a reasonably accurate calculation. The mass of an electron is 9.1 into 10 minus 31 kg. If its kinetic energy is 3 into 10 minus 25 joules. Calculate its wavelength. How do I do that? Well, see, mass of electron is 9.1 into 10 raised to minus 31 kg. Right. Kinetic energy I am given is 3 into 10 raised to minus 25 joules. Lambda de Broglie I am supposed to calculate. What is de Broglie wavelength? This is h by mv. H by, no, Can I relate momentum with kinetic energy? Yes, I can. Momentum mv is fine, and kinetic energy is half mv square, right? So could I say that this is 1 upon 2m mv the whole square? Yes. How much is this? Is k, right? And this is momentum p, so this is p square upon 2m. Therefore, momentum p is equal to root of 2 into m into kinetic energy. So instead of momentum, I could substitute under root 2 into mass of electron into its kinetic energy. Wow, this is really beautifully ugly. Yes, cheap, dirty calculations, but they're useful. Let's do them. So lambda de Broglie is H. H is 6.626 into 10 raised to minus 34 joule second. Fine. Divided by under root 2m. Under root 2 into mass of electron is 9.1 into 10 raised to minus 31 kg. Fanciful. And kinetic energy is how much? 3 into 10 raised to minus 25 joules. Kill me. This is what I have. Well, I guess we will live. Let's do more calculations. How much does that give me? The most beautiful part about atomic structure is it makes you go through a hell of a calculations and makes you mathematically very active in case you do all the calculations till the end, and you must do them till the end, right? So 31 and 25, that means 56. Root of 56, that half of 56 would be 28. 28 and 34, that would make it 10 raised to minus 28, 34, 10 raised to minus 6. Okay. And what else do I have? I have 6.626 divided by dirty root, that is 9.1 into 6. 6 1 is 6, 9 6 is 54. This is all I have. So many meters. Fine. Under root 54. If you want me to calculate approximately, under root 49 would be 7. Under root and 7.5 square would be 56.25. It's very close. It is around 7.4. So this is approximately 6.626 by 7.4 into 10 raised to minus 6 meter. If I shift the decimal, 7 meter. 66.26 by 7.4. Now 7 9s are 63. It's roughly around 8. Somewhere between 7 to 9, a number would be there. Yeah, roughly around. This is what I get. 8.9 into 10 minus 7 meter. Calculate this happily, and this is what you ultimately land with. Which of the following are isoelectronic species? That is, those having same number of electrons. All you are supposed to do is count the number of electrons. See, sodium, neutral sodium has 11 electrons. Okay. So Na plus has 11 minus 1, that is 10 electrons. Neutral potassium has 19. So K plus has 18. Mg magnesium has 12, plus 2 has minus 2, which is 10. Calcium has 20, minus 2, which is 18. Sulfur has, 16 electrons, and minus 2 means you have 2 more electrons. Minus charge means you have added electrons. Plus charge means you have subtracted electrons. Please remember that. So I have 18 electrons. And argon itself by default walks around with 18 electrons. So which are isoelectronic species? Sodium and magnesium. They have 10 electrons each and they are isoelectronic with each other. At the same time, potassium, calcium, sulfide and argon, they have 18 electrons each, and all these 4 species are also isoelectronic with each other. As simple as that. What is isoelectronic species? Species which have same total number of electrons are said to be isoelectronic, and here we have isoelectronic species. Write the electronic configurations of the following ions. We have hydride ion. Now hydrogen is 1s1. And hydride ions means negative charge means I have added one more electron. So I have added one more electron, that means now it is 1s2. Why? 1 plus 1, 2. 1s2. Na plus, sodium itself had, helium, which is 1s2, 2s2, 2p6, 3s1. This is sodium. If you want to make it sodium plus, well, you have to remove one electron, and this becomes helium, 2s2, 2p6. That's it, which is as good as neon. Wow, it has a noble gas configuration? Yes, it does possess a noble gas configuration. What about oxide ion? Well, oxygen itself is 1s2, 2s2, 2p4. Minus 2 charge means add 2 electrons. Electrons are negative, so when they are added, they give you minus charge. Minus 2 charge means you have to add 2 electrons. So now it becomes 1s2, 2s2, 2p6, which again is as good as neon. Lovely. What about fluorine? Fluorine itself is 1s2, 2s2, 2p5. And F minus means add 1 minus 1 charge means 1 electron. So you have 1s2, 2s2, 2p, 5 plus 1, which is 1s2, 2s2, 2p6, which is again as good as neon. These are, my dears, the electronic configurations of hydride, sodium oxide and fluoride ions. What are the atomic numbers of elements whose outermost electrons are represented by? Well, 3s1. Now 3s1, look at this. S means it is S block. 1 means it is group 1. And 3 means it is third period in periodic table. So if you want to figure it out in terms of periodic table, well, this is your chance. I'm talking about sodium here. Third period, first group, this is sodium. 2p3 and 2p5, this is P block, right? 2p means second period. And now tell me 3p would mean third period. And P3, this term 3, what does this term 3 reflect? This would give you P3 means now P block begins with group 13. So 13, 14, 15. So this is 15th group. Wow. 15th group is nitrogen. Yes, so we are talking about nitrogen. P5. P5 would refer to group 17. Halogens, yes. Third period halogen, we are talking about chlorine. Yes, we are talking about chlorine. This is how you get chlorine. Which atoms are indicated by the following configurations? Helium 2s1. Wow, this is lithium. By S block, group 1. This is P block. 3 means, now group number in P block, you can say in P block, group number is 12 plus this number. Whatever is the number of electrons in P block. 3 to 12 plus 3, 15. So this is third period. Group 15. Third period, group 15. Group 15 is nitrogen family. Third period, this is phosphorus we are talking about. For phosphorus, yes. What about this one? D block. Oh wow, yes. 4s2, 3d1. In D block, D1 would mean group 3. Group 3, we are talking about scandium. This is scandium. 4s means fourth period. D means D block. D block, fourth period, first element, scandium. This is scandium. What is the lowest value of N that allows G orbitals to exist? Wow. We have 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Please note there cannot be 1p orbital or 2d or 3f. For p orbitals, the minimum value of n is 2. For d orbitals, minimum value of n is 3. For f orbitals, minimum value of n is 4. Similarly, 5s, 5p, 5d, 5g, 5f and 5g. So minimum value of n for which g orbitals can exist is 5. An electron is in one of the 3 d orbitals. Okay, give the possible value of n, l and ml for this electron. Well, the moment you say 3d, n is fixed. N is 3. D orbitals mean L is equal to 2 for D orbitals. And possible values of ML. Now ML can be minus L to 0 to plus L. That means ML can be minus 2, minus 1, 0, plus 1, plus 2. There are 5 possible values of ML or magnetic quantum number. An atom of an element contains 29 electrons and 35 neutrons. Oh my God. So, deduce the number of protons and the electronic configuration of the element. Now, number of protons is equal to number of electrons, which is 29. Oh wow, that's simple. Yes. So, number of protons is 29. We have one answer. Because an atom is neutral, so number of electrons must be equal to number of protons. Yes. And secondly, the electronic configuration of the element. Do we have electronic configuration of the element? Yeah, there could be. What is electronic configuration? Now, since number of electrons is 29, let me start writing. Well, this is neon. Till neon, we have 10 electrons. I mean, 1s2, 2s2, 2p6. This is neon. And we have 10 electrons. Then 3s2, 3p6. Well, that is actually till argon. We have 18. Now 4s2, we have 20. And then we should have 3d9. Oh my God. D orbitals were about to be filled. There is an exception. What? Instead of this, I should write it as 4s1, 3d10 because there is extra stability associated with fully filled d orbitals. This is copper we are talking about, it seems. So what is the electronic configuration? Well, it is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. This is the way we say it. In short, this can also be written as argon, 3d10, 4s1. This is the required electronic configuration. Give the number of electrons in the species H2+, H2 and O2+. How do we calculate that? Well, we know hydrogen. Hydrogen has 1 proton, so it must have 1 electron. And H2 would contain 1 plus 1, and that is 2 electrons. So H2 contains 2 electrons. And H2 plus means 1 electron is removed from H2. But H2 already contained 2 electrons. So 2 minus 1, that is 1 electron in H2 plus. Please note, if you have plus charge, you have removed electron. What about, so this is done. This is 1, this is 2. What about oxygen? Oxygen contains 8 protons and 8 electrons. So O2 contains 8 plus 8, 16 electrons, and O2 plus contains 16 minus 1, which is 15 electrons. That's it.